If you take an organic acid, let's call it something generic, such as HA, and you dissolve it in water, so we're going to dissolve this acid in water. Some of the acid will dissociate, giving up its proton. And so if we draw the curved arrow notation for that, it would simply be the lone pair on the water molecule would grab the proton. This is actually attacking an unfilled sigma star of the HA. And then we're going to break the HA sigma bonds, moving the electrons onto A. And so in this case, we form in water what's called a hydronium ion. You guys should be thinking about the formal charge here on the oxygen. It's going to be 1, 2, 3, 4, 5. So 6 minus 5 is plus 1. And then because A now has an extra lone pair of electrons, it's going to be A minus. Some basic terminology to keep in mind. If we call HA the acid, whenever an acid loses a proton, it forms what's called the conjugate acid. Sorry, let me say that one more time. When an acid loses a proton, it forms what's called a conjugate base, which in this case is A minus. Now the base in this reaction is actually the water. And so if we define the base to be on this side of the equation, what you form when you grab a proton is called the conjugate acid. This equilibrium arrow denotes that the reaction is reversible. So you guys can also imagine that A minus can come, grab a proton from the conjugate acid, and then regenerate water and HA. And so this equilibrium is what we're really looking at and what we're trying to quantify. So just as a reminder, we're going to define the equilibrium as Ka is equal to the concentration of H3O plus times the concentration of A minus divided by the concentration of HA. And in this case, water is the solvent, so it's relatively constant. And so we're going to ignore that. And this is going to be called the acidity constant. So if you imagine if HA is a super strong acid, then the Ka will be relatively high, right? Whereas if it's a weak acid, the Ka will be small. In general, the Ka's sort of range. So Ka's usually equal somewhere between 10 to the minus 5 to 10 to the minus 50. So in this case, if something has a 10 to the minus 5 Ka, this would be on the stronger end of the organic acids. And 10 to the minus 50 would be one of the weaker organic acids. So because of this relationship, we also are going to define what's called a pKa. And the pKa is equal to the negative log of the Ka. And so based on the scale, you guys can see that pKa's will range from -5 to up to 50. Right? In this case, the lower the pKa, the stronger the acid. The stronger the acid here. Now, our textbook has some different pKa values for us, and I've also given you in my course notes a chart of pKa values that I suggest you commit to memory. This was really super helpful on the final exam, and I asked students to know a few different pKa values just so you can get an idea of how strong organic acids are. And so we'll go through some of these in a bit, but this is definitely a chart that I would start committing to memory. It's going to allow you to predict organic reactions just based on the pKa values. Okay, so with that in mind, let's take a look at now some examples of acids. So last time we defined Lewis acid, Lewis base, Bronsted acid, and Bronsted base. And so I want to give you an example of a few acids. And this is from our textbook. This is figure 2.1. And so some of the common acids are, for example, HCl is a good acid. Hydrogen sulfuric acid, H2SO4. That's also a very good, strong acid. We can draw out the Lewis dot structure here. So these are inorganic acids. They don't have any carbon atoms in them. Other common acids, of course, water can act as an acid. And then also hydronium ion. Now we can also have organic acids, and you'll see some various ones during the class. Today we're going to focus on an organic acid called acetic acid, which we've also seen in class before. In regards to the inorganic bases, some common ones are water, ammonia, hydroxide, and amide. And so inorganic bases. Hydroxide is a very strong base. And this is even stronger. And then we can also have organic type bases. So just an example of some organic bases. These are going to be electron pair donors. So some common ones are methylamine, methoxide. So methylamine is CH3 and H2. Methoxide is a common one. And then we've also got compounds that are Lewis basic, such as acetone. This is not a very strong base, but the lone pair on the oxygen here are good lone pair donors. And so acetone can also act as a Lewis base. In addition to that, remember I talked about this idea of pi bonds being nucleophilic. Pi bonds are also Lewis bases, and so you can also have, for example, pi bonds acting as organic bases. So as I mentioned, most reactions are going to be basically a base reacting with an acid, and one of the challenges will be to identify which one's the acid and which one is the base in these cases. I also want to refer you guys to table 2.1 in your textbook for some examples of basically pKa values. So that's a super useful chart to look at. It shows us basically the acids involved and then the conjugate bases. And so just to show you here what I'm talking about, we pop up this book. Okay, so as you can see here, we've got HCl. That's one of the strongest acids that you'll see. It wants to give up its proton, and it can form a relatively stable conjugate base, the chloride ion. And so in this case, the pKa of HCl is very high. It's very low. It's all the way down at -7. In terms of organic acids, acetic acid is relatively strong as well. It has a pKa of 4.8. And it forms the conjugate base acetate anion. And we talked about how this anion is important example of an anion that's resonance stabilized. This explains actually why Acetic acid is way, way, way more acidic than water. If we deprotonate water with a pKa of 15.7, it forms a conjugate base called hydroxide, and this one is not resonance stabilized. Ethanol, you can imagine, very similar structure to water, kind of similar pKa's too, right? So similar functional groups will have similar pKa values. That's going to form a ethoxide, and it's also an anion that has a negative charge on oxygen, which is relatively electronegative. Now here again, these are just pKa trends. These are things that can be measured. We can look at acetylene, a molecule that we've looked at its structure in great detail. We've looked at the bonding in acetylene. For the exam, you guys should know things like how to draw the pi bonds. We've gotten some questions about this during the Facebook discussion. Basically, you have to show that the p orbitals are orthogonal to each other. So you can label your paper with XYZ, for example. And as long as you label things clearly, it should be fine. You guys can also bring colored pens to the exam just to color the orbitals differently if it makes it more clear. But we can see here that this is not a very strong acid at all compared to ethanol or water. To deprotonate the proton on acetylene, the pKa here is 25, and you generate an anion where there's a lone pair on the carbon now with a formal -1 charge, and this anion is called acetylide. Hydrogen's not very acidic, 35. Ammonia is not very acidic, right? To remove that proton, it's a pK of 38. And then one of the weakest acids that we come across here is methane itself, pKa of 50. So this table is really, really handy. It gives us an idea of the acidity of some of these things. And so your TAs, for example, will be eventually taking oral exams to go on to get their PhD degrees. And one of the things that they'll know is they'll know a lot of pKa's by heart, because this will allow them to predict the favorability of a chemical reaction. Right? So whether or not an acid-base reaction happens depends on whether or not the acid is strong enough to react with the base or vice versa. Okay, so this is a really great table, and I also made a flashcard for you guys that will help you memorize some of these pKa values. But possibly way more important than memorizing these values, they kind of give you an idea of the range we're talking about, is to start to rationalize why is it that, for example, acetic acid is such a strong acid compared to water or ethanol. So to do that, we're going to talk about 4 different effects that allow us to compare acids. And the key to this idea is that these effects are going to let you predict chemical equilibria. So as an example of that, let's take an example of an acid-base reaction that's actually from our textbook. So in this case, we're going to use this molecule, acetylene, as one of the components of the reaction. And we're going to react this with a base. In this case, we're going to react it with amide. So we've got NH, the negative charge on the amide, in equilibrium. And so you guys should be able to now think about, between these two molecules, this one is negatively charged, so there's a clue that this is the electron-rich or Lewis basic part of the reaction. And then here we have the CH bond, that's going to be the Lewis acid. Or in this case, it's also a Bronsted acid because it's a proton donor. Okay, so what will happen is the amide will attack, and you're going to break the sigma CH bond, putting a lone pair on the carbon. And so acetylide will form a conjugate base, acetylene here, will form a conjugate base called acetylide. Plus the amide will turn into the conjugate acid, ammonia. Okay, so on an exam, for example, if I asked you to label these, you would label this one the acid, this one the base. This one's going to be called the conjugate base, and here we have the conjugate acid. Now, in order to predict which side of this equilibrium is favored, you can actually use just pKa values. So thinking back about that chart that we just went over, if you guys can kind of try to recall the pKa of the acids here, the pKa of ammonia, you guys remember, is about 38. And the pKa of acetylene, based on the table that we just looked at, was what? That's about going to be 25. And so comparing these two acids in the equilibrium, the question now becomes which side of this equilibrium is favored. You guys are really quiet out there today, but we can have a vote with the 3 students that are actually here. So which side of this equilibrium do you guys think is favored? All right, so we've got one side that has a formation of an acid that has a pK of 25, and the other side has an acid formation of pK 38. So comparing these two acids, which side makes the weaker acid? Is acetylene a weaker acid or ammonia? Okay, so step 1, we can identify here the weaker acid has the higher pKa. Right, so in this case, NH3 is weaker. And then in step 2, we can predict that the equilibrium favors formation of the weaker acid. So you guys can think of it as, you know, if somebody wants to really give up their proton, they're going to form a relatively stable anion, and they're going to make an acid that is very weak and doesn't want to give up its proton. Right? So in comparison to acetylene, ammonia doesn't have a strong propensity to give up its proton. It's weaker. And so it's going to hang on to that proton more strongly in the thermodynamics of this system. Okay, so it makes sense that the equilibrium is going to favor the weaker acid. It's going to favor the formation of the happier, more stable conjugate base. Okay, so with this simple idea and some pKa values, you guys now have the power to predict chemical equilibria. And as I stated, on Wednesday, you're going to practice a whole bunch of these problems, predicting chemical equilibrium based on pKa values and this idea that you're going to favor formation of the weaker acid, the acid where the proton is held on more strongly. Okay, so that's section 2.4, predicting acid-base equilibrium. Now, what I want to go over next is just 4 effects, these 4 effects that also make up 4 out of the 133 concepts I want you to master in this class. And I'm going to go a little bit out of order from our textbook because I want to start with what I think is one of the most important effects, and we already talked about this last time, and this is the resonance effect. So if you ever have a system that can have resonance stabilization, this effect is going to win out. Okay, so this is one of the most important effects. And as a reminder, this effect says that delocalization of a charge stabilizes it. So for example, when we compare two anions, the acetate anion with a -1 charge versus, for example, just an alkoxide anion, here this charge is localized. So this is not as stable. Whereas in this charge, it's going to be spread out between both oxygen atoms. And so it's a much more stable anion. Right, and so here you can predict that this is more stable. This one is more basic or reactive. So that's a reminder of the resonance effect. But how are we going to use these effects? So some things, there's actually a set of rules that I also put in your flashcards. And these rules are super important in terms of the logic that you're going to use in order to compare two acids. Okay, so rule number one. So when comparing two acids, and trying to figure out which one is more stable. Let's say you're comparing acetic acid versus ethanol. This is the thing about the logic. It's really kind of hard to just look at two structures and compare them, because what we're trying to compare is a thermodynamic value, right? pKa, equilibria. And so the very first step in order to do this, step one, is instead of just comparing the acids, you're going to draw the conjugate bases. Right? So you're going to draw the structure that results from deprotonation of these acids. So that's step one. After you draw that, you're going to determine which base is more stable. So that's going to be step two. You ask yourself, which base is more stable? And you're going to ask this question based on four effects: resonance, elemental, hybridization, and does anyone remember the last one? Starts with an I, inductive. After you determine which one is more stable, you can use this logic. So if I'm a very acidic acid, I want to give up a proton, I'm going to form a very happy, stable base. So the more stable the base, the more stable the conjugate base, the more acidic the acid. So here's the logic we use. The more happy the conjugate base, the more acidic the acid. Right? That kind of makes sense, because if an acid is really strong, it's going to really want to give up its protons. And it's going to form a conjugate base that's really happy, stable, being an anion. Okay, this is the key logic that you're going to use. You always have to use this logic. Students will kind of get themselves in trouble if they try to skip these steps and just try to predict which one is more of a strong acid just by looking at it. And so one way you can think about this, here's an analogy for you. If there's two people and you're trying to figure out which one loves chocolate more, right? So you give chocolate to both of them. And then you remove the chocolate, and then you see which person is more angry and unhappy, right? So the person that's angrier and unhappier is probably the one that really loves the chocolate even more. Whereas the person that's totally fine and happy without the chocolate, they're the more sort of happy conjugate base, right? So they're willing to give up that chocolate. Okay, so the key is you've got to look at the effect after you give up the proton, and not just comparing these two guys beforehand. So using this logic, we can go back here and see, like, what I did was I drew out the anions. So I did step one. And then I asked myself which one is more stable, and it was definitely the acetate. And so now the question is, which one is more acidic? Okay, so let's think about this. The logic here is the more happy the conjugate base, the more acidic the acid. And so acetate was much more stable because of resonance. And so acetic acid is, in fact, a lot more acidic. And this is also played out if we look at the pKa values, right? So I would memorize some of these. pKa of this one, 16. pKa of acetic acid, 4.8. Okay, so this is always the logic that we're going to use when looking at this idea of comparing two acids. Okay, so let's take another example now. And we're going to compare two acids, and this will become more clear when we look at the what's called the elemental effect. So we're going to compare a molecule called methanol versus methane. Okay, so which one do you guys think is more acidic, methanol or methane? And this is without knowing the pKa values, right? So again, I'm going to apply this three-step logic. Step one is I'm going to draw the conjugate base of each. So CH3O negative. This is called methoxide. And then I'm also going to draw the conjugate base of methane, where I've removed a proton. And so now I have a carbon anion, with a negative charge. So step one, draw the conjugate base. Step two, ask which conjugate base is more stable. Now this effect is actually pretty huge as well. There's no resonance in these structures. These are actually two completely different elements. We're comparing O minus versus C minus. Which one's more electronegative, oxygen or carbon? Well, oxygen is more electronegative. So it stabilizes the positive charge better. Sorry, it stabilizes the negative charge better. All right, so by that logic, this means that the methoxide anion is way more stable than the carbanion, because oxygen is way more electronegative than carbon. And so in comparing these two, this tells me that methoxide is a more stable, it's a happier base. And so the logic here would be to say in step three, methanol is more acidic. Okay, so that's the elemental effect. You actually compare the element that the negative charge is on, so oxygen versus carbon. Now, these pKa values are pretty dramatic. Here the pKa of methanol is about 16, and this is a super weak acid, pKa of 50. So resonance effects is important if both of the elements are the same. So if it's two oxygen anions, two nitrogen anions, two carbon anions, the resonance effect is going to win out. But it's really easy to compare two acids when they're attached, when the proton is attached to two completely different elements. And so this elemental effect actually charts really well with the periodic table, right? So just to take some examples here of the elemental effect, going across a periodic table. I can have my CH bond, my NH, OH, and then all the way at the end here, you know, an FH, or we usually write it HF. Those are acidity trends going across the periodic table, and we also know some pKa values, right? So again, I would memorize some of these. They're not too hard, and these are probably one of the only numbers that you really have to memorize. So 50, pKa of 38, pKa of about 16, and then HF is a pretty strong acid, pKa of 3.2. And so going across the periodic table here in our trend, we can see that the acidity increases. And what's the logic behind that? Well, the logic is you're going to draw out the conjugate base, so C minus O minus, N minus, F minus. As you guys look at these conjugate bases, the stability increases going this way due to electronegativity of the element. Okay, so this is also a super powerful effect. You can compare two acids by looking at the element to which that proton's attached, right? So you can automatically tell that something like a CH bond is going to be way less acidic than an NH or an OH or an HF. If I compare an NH versus an OH, I know that the OH is going to be way more acidic than the NH. Okay, and that's all based on the electronegativity of this atom. Oh, it looks like my screen froze here. Okay, so sorry about that. The screen kind of froze. But what you guys can see here is I drew out the pKa's, so 50, 38, 16, 3.2. And then I drew out the conjugate bases, so C minus, N minus, O minus, F minus. And these conjugate bases become more stable going across the periodic table towards F minus, due purely based on electronegativity. Okay, so the elemental effect, super powerful way to compare two bases two acids if they're connected, if the proton's connected to a different element. Okay, so that's section 2.54 in our textbook. Now, you guys can also compare things going down a periodic table as well. So, for example, HF versus HBr. But the trend is a little bit counterintuitive, right? Because you might think, well, all right, Professor Dong, you said that the anion, if it's more electronegative, it's more stable. But if we compare these acids, HF versus HBr, there's actually something more important than electronegativity. So going down the periodic table, HF versus HCl versus HBr versus HI. The pKa's actually increase. They become more negative, sorry. So negative 10, negative 9, negative 7. So here, and we know this was around 3.8, 3.2. Okay, so what's happening here? Well, even though electronegativity is actually decreasing, what happens is the anions become bigger. So the size kind of wins out over electronegativity. Right, so I minus is actually better able to sort of carry that negative charge because it's a very big polarizable atom. Right, so I minus is actually a relatively stable anion due surely to its size and polarizability. Whereas F minus is not such a happy stable anion because there's a lot of negative charge that's localized on this very small atom. Okay, so going down a periodic table, the size is more important, and that's how we can compare these trends. All right, guys, so we're going to talk about another effect. Remember I said there's 4 different effects that we're going to go over. And this next one is section 2.5. It's called the inductive effect. So this is also one of our key concepts to master. And when we think about the inductive effect, it's basically this idea that we are pulling electron density through sigma bonds. And so a quick comparison would be ethanol versus trifluoroethanol. CH3, CH2, OH. versus CH3, CH2OH. Where instead of CH3 here, we're going to put CF3. So due to the electronegativity of these fluorine atoms, when we draw the conjugate acids, and compare these two conjugate bases, we'll see that this conjugate base here is more stable because there's an inductive effect where the carbene-fluorine bonds help stabilize the negative charge because they're pulling electron density through the sigma bonds. Okay, so this is more stable due to the electronegative CF3 groups. And so in step 3, you can predict that this guy is also going to be more acidic. And we can see this effect bear out if we compare the pKa values. So ethanol has a pKa of 16, and trifluoroethanol has a pKa of 12.4. Okay, so the last effect that I'm going to talk about is going to be what's called the elemental effect, and it's this hybridization effect. And so in this case, actually, we're going to have your TAs discuss this effect on Wednesday in lecture. But the most important thing to take home from this lecture is this 3-step process. Whenever you're comparing two acids, the first thing to do is draw out the conjugate bases. Compare those two conjugate bases, asking yourself which one's more stable, and then you can go back and rationalize that the stronger acid forms the more stable conjugate base.